Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The zone where life could exist. Life as we know it requires certain conditions to exist. Too hot and water boils away. Too cold and water freezes solid. Without liquid water, life as we understand it cannot survive, at least not the kind of carbon-based, water-dependent life that evolved on Earth. This simple requirement creates a critical region around every star called the habitable zone, sometimes nicknamed the Goldilocks zone because conditions there are neither too hot nor too cold, but just right for liquid water to exist on a planet's surface. Understanding this zone and what makes it special reveals both the requirements for life and the astonishing variety of places in the universe where life might possibly emerge. The habitable zone is not a single precise distance from a star, but rather a range of distances, a band extending outward from the star where temperatures allow water to remain liquid. For our Sun, this zone extends roughly from about 90 million kilometers to about 150 million kilometers from the Sun. Earth, orbiting at about 150 million kilometers, sits comfortably within this zone, though closer to the inner edge than the middle. Venus, at about 108 million kilometers, orbits just inside the inner edge, where temperatures are too high. Its surface temperature exceeds 450 degrees Celsius, hot enough to melt lead, far too hot for liquid water. Mars, at about 230 million kilometers, orbits near or just beyond the outer edge, where temperatures are generally too cold. Though liquid water might occasionally exist in certain locations under special conditions. The boundaries of the habitable zone depend entirely on the star's properties. Hotter, brighter stars have habitable zones located farther out because their intense radiation heats planets to higher temperatures. Cooler, dimmer stars have habitable zones located much closer in. A red dwarf star, the most common type of star in the galaxy, might be only 1/10 as luminous as the Sun, meaning its habitable zone would be about 1/3 the distance from the star. A planet orbiting in the habitable zone of a red dwarf might orbit only 10 million kilometers from its star, closer than Mercury orbits our Sun, yet still maintain temperatures suitable for liquid water because the star is so much dimmer. The habitable zone also depends on the planet's atmosphere. A thick atmosphere with greenhouse gases can trap heat and keep a planet warm even if it orbits farther from its star than the outer edge of the simple, habitable zone. Venus demonstrates the opposite effect. Its extremely thick carbon dioxide atmosphere creates a runaway greenhouse effect, trapping heat so efficiently that surface temperatures soar far beyond what you would expect from Venus's distance from the Sun alone. Without this greenhouse effect, Venus might be cool enough for liquid water. With it, the planet is an inferno. Mars provides another instructive example. Mars orbits near the outer edge of the Sun's habitable zone, and its thin atmosphere, less than 1% the pressure of Earth's atmosphere, cannot retain much heat. Surface temperatures average around -60 degrees Celsius, far too cold for liquid water most of the time. But billions of years ago, Mars had a thicker atmosphere and likely had liquid water flowing on its surface, creating the river valleys and lake beds that spacecraft have photographed. Mars lost most of its atmosphere over time, probably because its weak magnetic field couldn't protect the atmosphere from being stripped away by the solar wind. The planet moved out of effective habitability not by changing its orbit, but by losing the atmosphere that kept it warm. Earth maintains liquid water on its surface through a fortunate combination of factors. Our distance from the Sun provides a baseline amount of heating. Our atmosphere, with modest amounts of carbon dioxide and water vapor, acting as greenhouse gases, traps enough heat to raise the surface temperature by about 33 degrees Celsius, above what it would be without an atmosphere. Our magnetic field, generated by the liquid iron core's motion, shields the atmosphere from the solar wind, preventing the atmospheric loss that doomed Mars. Our planet's size gives it enough gravity to hold onto its atmosphere over billions of years. But the habitable zone is more complex than just distance from a star and atmospheric composition. Other factors influence whether life could actually emerge and survive. Planetary mass matters. A planet too small cannot retain an atmosphere because its weak gravity allows atmospheric gases to escape to space. A planet too large might have such a thick atmosphere that surface pressures become extreme, or might retain so much hydrogen and helium from its formation that it becomes more like a miniature gas giant than a terrestrial world. The planet's rotation rate influences habitability as well. A planet that rotates very slowly, or is tidally locked to its star, showing the same face always toward the star as the Moon does to Earth, would have extreme temperature differences between the permanent day side and permanent night side. The day side might be too hot for liquid water, while the night side freezes. Venus rotates extremely slowly, taking more than 200 Earth days to complete one rotation, though its thick atmosphere distributes heat efficiently enough that temperatures are fairly uniform across the planet, despite this slow rotation. Stellar variability affects the habitable zone's stability over time. The Sun's luminosity has increased by about 30% over its lifetime. Early in Earth's history, when the Sun was dimmer, Earth received less heat. Yet geological evidence shows that liquid water existed on Earth's surface going back nearly 4 billion years, despite the fainter Sun. This is called the faint young Sun paradox. The solution probably involves a thicker atmosphere with more greenhouse gases in Earth's past, compensating for the dimmer Sun and keeping temperatures warm enough for liquid water. As stars age, their habitable zones move outward. The Sun will continue brightening over the next billion years or so. Eventually, perhaps in 1 billion to 1.5 billion years, the Sun will become bright enough that even with our current atmosphere, Earth's surface will become too hot for liquid water. The oceans will evaporate, water vapor will accumulate in the atmosphere, and the increased greenhouse effect will push temperatures even higher in a runaway process. Earth will exit the habitable zone, not because Earth moves, but because the habitable zone moves outward as the Sun brightens. Subsurface habitability expands the possibilities beyond the traditional habitable zone. Moons orbiting gas giant planets can have liquid water beneath their icy surfaces, even if they orbit well outside the star's habitable zone. Jupiter's moon, Europa, and Saturn's moon, Enceladus, both have subsurface oceans kept liquid by tidal heating, the gravitational squeezing from their parent planets that generates internal heat. These moons demonstrate that life might not require surface liquid water or even a planet within the traditional habitable zone. The requirements might simply be liquid water somewhere, an energy source, and the right chemical ingredients. Tidal heating expands the possible locations for life significantly. A planet or moon doesn't need to orbit at a specific distance from its star if internal heat from tidal forces can keep subsurface water liquid. This might be particularly important for moons orbiting planets in the habitable zones of red dwarf stars, where tidal locking to the star might make surface habitability challenging, but subsurface oceans remain possible. The chemical composition of the planet matters as much as its location. Life requires more than just water. It needs raw materials. Carbon, nitrogen, phosphorus, sulfur, and trace amounts of many other elements are essential for the biochemistry we know. Planets that form too close to their star might lack volatile elements like carbon and nitrogen that are essential for life. Planets that form too far out and then migrate inward, might have compositions dominated by ices, rather than having the right balance of rock, metal, water and organics. Stellar type influences habitability in ways beyond just temperature. Red dwarf stars, while having habitable zones close in, pose challenges for life. These stars frequently produce powerful flares, sudden bursts of radiation, and charged particles that could strip away planetary atmospheres and damage biological molecules. A planet in the habitable zone of a red dwarf would need a strong magnetic field to protect against this radiation. Additionally, red dwarfs are so dim that their habitable zone planets likely become tidally locked, always showing the same face to the star, which creates the extreme temperature contrast problem. More massive stars, while having habitable zones farther out, present a different problem. They burn through their fuel quickly and don't live long enough for complex life to evolve. A star twice the Sun's mass might only live a few billion years before exhausting its hydrogen fuel and evolving into a red giant. On Earth, simple life emerged fairly quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. More massive stars might not remain stable long enough for complex life to evolve on their planets. Binary star systems where two stars orbit each other create more complicated habitable zones. If the stars orbit close together, planets might orbit far enough from both stars that the pair acts like a single brighter star, creating a habitable zone at a large distance. If the stars are widely separated, planets might orbit just one star in a habitable zone, determined primarily by that star's properties. But intermediate cases, where the stars are separated by distances comparable to their habitable zones, create complex and potentially unstable conditions for planets. The galactic habitable zone adds another layer of consideration. Different regions of the galaxy have different properties relevant to life. Near the galactic center, stars are packed more densely, and supernova explosions occur more frequently, potentially sterilizing planets with intense radiation. Far in the outer reaches of the galaxy, stars might be too poor in heavy elements to form rocky planets with the chemical complexity needed for life. The region where our Sun orbits, about halfway out in the galactic disk, might represent a galactic habitable zone where conditions are most favorable for life to emerge and survive long term. Exoplanet discoveries have found thousands of planets, many within their star's habitable zones. Proxima Centauri b, orbiting the nearest star to our Sun, sits within its star's habitable zone, though whether it actually has liquid water and a protective atmosphere remains unknown. Kepler and other missions have found dozens of roughly Earth-sized planets in habitable zones, though determining which of these might actually host life requires detailed atmospheric studies that current telescopes can barely begin to perform. The concept of habitability continues evolving as we learn more about the diversity of planetary environments. Life might exist in forms very different from Earth's biology, adapted to environments we would consider extreme. Subsurface oceans beneath ice shells, atmospheres of exotic chemistry on planets very different from Earth, even clouds in the atmospheres of gas giants. All these represent potential habitats that expand the zone where life might exist far beyond the simple band of distance where liquid water exists on a planet's surface. The habitable zone represents our best current understanding of where to look for life, based on the one example we have: Earth. It's a starting point, a place to begin the search, knowing that life's possibilities might extend far beyond this simple definition. The zone where life could exist might be much larger than we imagine, encompassing not just planets at the right distance from their stars, but moons with tidal heating, planets with exotic chemistries, and environments we haven't yet conceived, each one a potential home for biology waiting to be discovered. What is dark matter, and why can't we see it? Imagine trying to understand a conversation in a crowded room while wearing earplugs. You can see people's mouths moving, see their gestures, watch them react to each other, but you can't hear the words being spoken. You know communication is happening, the evidence is clear in the movements and responses, but the medium of that communication remains completely inaccessible to you. This is somewhat like humanity's relationship with dark matter. We can see its effects throughout the universe, observe how it shapes galaxies and bends light, measure its gravitational influence on everything around it, yet the substance itself remains invisible and intangible to every instrument we've built to observe the cosmos. Dark matter makes up approximately 85% of all matter in the universe. Let that sink in for a moment. Everything you can see, every star, every galaxy, every glowing nebula, every planet, every atom in your body represents only about 15% of the matter that exists. The rest, the overwhelming majority, is dark matter, and it surrounds us, permeates us, flows through us, yet reveals itself only through its gravitational effects. The story of dark matter's discovery begins not with a sudden revelation, but with decades of observations that didn't quite make sense. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a collection of over 1,000 galaxies bound together by gravity. He measured how fast these galaxies were moving within the cluster and used these velocities to calculate how much mass must be present to keep the cluster gravitationally bound. What he found was shocking. The galaxies were moving so fast that they should have escaped the cluster's gravity and flown apart long ago, unless the cluster contained far more mass than could be seen in the form of stars and gas. Zwicky proposed that some form of dark matter must exist, matter that didn't emit light, but provided the additional gravity needed to hold the cluster together. His idea was largely ignored for decades. It seemed too radical, too strange. Surely there was a simpler explanation. Perhaps astronomers were just missing some normal matter, dust clouds or dim stars that hadn't been detected yet. But the evidence kept accumulating. In the 1970s, astronomer Vera Rubin conducted detailed studies of how stars and gas move within spiral galaxies. According to the laws of gravity and orbital mechanics, objects farther from the center of a galaxy should move more slowly, just as planets farther from the Sun orbit more slowly than those closer in. Mercury races around the Sun in just 88 days, while distant Neptune takes 165 years to complete one orbit. The same principle should apply to galaxies. Stars near the edge should crawl along in their orbits compared to stars closer to the galactic center. But that's not what Rubin found. She observed that stars at the outer edges of galaxies move just as fast as stars closer to the center, sometimes even faster. The rotation curves of galaxies were flat rather than declining, which could only mean one thing. There was far more mass in these galaxies than could be accounted for by visible stars and gas. And this extra mass wasn't concentrated at the center where most of the visible matter was. It extended far beyond the visible disk, forming a massive spherical halo of invisible matter surrounding each galaxy. Picture a galaxy in your mind, a spiral with graceful arms of stars spinning around a bright central bulge. Now imagine that entire visible structure is embedded within a much larger sphere of dark matter, extending perhaps 10 times farther than the visible stars reach. This dark matter halo contains several times more mass than all the stars, gas and dust combined, yet it emits no light, no radio waves, no X-rays, nothing we can detect directly. The evidence for dark matter extends far beyond galaxy rotation curves. Gravitational lensing provides some of the most compelling proof. According to Einstein's theory of general relativity, mass warps the fabric of spacetime, and light follows the curves in this warped spacetime. When light from a distant galaxy passes near a massive object, its path bends. Just as light bends when passing through a glass lens. The amount of bending depends on how much mass is present, Astronomers observe light from distant galaxies being bent and distorted as it passes through galaxy clusters. By measuring this distortion carefully, they can map out exactly where mass is concentrated in these clusters, creating what's essentially a gravity map. When they do this, they find that most of the mass, about 90%, isn't where the visible galaxies are. It's distributed in a much larger structure, consistent with massive halos of dark matter. One of the most dramatic examples came from studying a structure called the Bullet Cluster, where two galaxy clusters had collided and passed through each other. During the collision, the hot gas from each cluster, which is normal matter, slowed down and remained near the collision site, heated by the impact. But the dark matter from each cluster, which doesn't interact with normal matter except through gravity, passed right through and continued moving. By mapping the gravity through gravitational lensing, astronomers could see that most of the mass had separated from the visible gas, providing direct evidence that dark matter and normal matter are distinct substances. So what is dark matter made of? This is one of the deepest mysteries in physics. And the honest answer is that we don't know. We know what it isn't. It's not made of atoms, protons, neutrons, or electrons. It's not any form of normal matter that we're familiar with. We call normal matter baryonic matter, and dark matter is something entirely different, something that exists outside the catalogue of particles that make up everything we can touch and see. The most popular hypothesis is that dark matter consists of particles that simply don't interact with electromagnetic radiation. Light, radio waves, X-rays, any form of light across the entire spectrum. These hypothetical particles, often called WIMPs, weakly interacting massive particles, would have mass and exert gravity, but they wouldn't emit, absorb, or reflect light. They would be essentially transparent to electromagnetic radiation, which is why we can't see them. Imagine a particle that could pass through matter almost as if it weren't there. Billions of these particles might be flowing through your body right now, passing through the Earth, streaming through space, and you would never know. They don't collide with atoms, don't scatter off electrons, don't leave any trace except for their collective gravitational influence. This is what dark matter particles would be like. Ghost particles that fill the universe, but interact with normal matter only through the weakest of forces. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and background radiation, trying to catch the rare interaction of a dark matter particle with normal matter. These detectors contain tanks of specially purified materials, cooled to near absolute zero, instrumented with sensors that can detect the tiniest energy deposit. The idea is that occasionally, very rarely, a dark matter particle might collide with a nucleus in the detector, releasing a tiny amount of energy that could be measured. So far, despite decades of searching with increasingly sensitive experiments, no one has definitively detected a dark matter particle. Another possibility is that dark matter consists of primordial black holes that formed in the early universe, not from collapsing stars, but from density fluctuations shortly after the Big Bang. These would be dark by their very nature, since black holes don't emit light. However, careful observations suggest that primordial black holes can't account for all the dark matter. They would produce observable effects, like gravitational microlensing when they pass in front of distant stars. And we don't see these effects at the level that would be expected if most dark matter were in this form. Some theories propose that dark matter might be axions, extremely light particles that were produced in enormous quantities in the early universe. These would be very different from WIMPs, much lighter, much more numerous, behaving more like a wave than individual particles. Detecting axions requires different experimental approaches, and several experiments are currently searching for these elusive particles. There's even a possibility though most physicists consider it less likely, that dark matter doesn't exist at all. Instead, perhaps our understanding of gravity is incomplete, and the theory needs to be modified to explain the observations without requiring invisible matter. These modified gravity theories, called MOND, modified Newtonian dynamics, and various relativistic extensions, can explain some observations but struggle with others, like the bullet cluster, which seems to require actual dark matter to explain. Dark matter played a crucial role in the formation of structure in the universe. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny variations in density. These variations were the seeds of all future structure: galaxies, galaxy clusters, and the cosmic web. But normal matter coupled to radiation in the early universe couldn't collapse and clump together efficiently. Dark matter, which didn't interact with radiation, could begin collapsing earlier, forming gravitational wells that normal matter eventually fell into. Without dark matter, galaxies as we know them couldn't have formed in the time available since the Big Bang. Today, dark matter continues to shape the universe. It forms the gravitational scaffolding along which galaxies are distributed. It determines how galaxy clusters form and evolve. It affects how galaxies merge and interact. Every large-scale structure in the universe exists because of dark matter's gravitational influence. On smaller scales, dark matter fills our own galaxy. The Milky Way sits within a dark matter halo that extends far beyond the visible disk of stars. This halo contains perhaps 10 times more mass than all the stars in the galaxy. As our solar system orbits the galactic center, we're moving through this sea of dark matter. At any given moment, thousands of dark matter particles might be passing through every cubic centimeter of space, though detecting even one of them remains beyond our current capabilities. The invisibility of dark matter is not a limitation of our instruments. It's a fundamental property of the substance itself. We can't see it because it doesn't interact with light in any way. We can't build a better telescope or a more sensitive camera to observe it directly. The only way we know it exists is through its gravitational effects on the things we can see. It reveals itself in the motion of stars, the bending of light, the structure of the cosmic web, and the evolution of the universe itself. Dark matter surrounds us, shapes the cosmos, and yet remains one of the deepest mysteries in science, a reminder that the universe is far stranger and more complex than our everyday experience might suggest. What comets are really made of? Comets have captivated human imagination for millennia, appearing in the sky as ghostly visitors with long tails that stretch across the heavens. Ancient civilizations often viewed them as omens or messengers from the gods. But these cosmic wanderers are not supernatural phenomena. They're physical objects composed of specific materials that reveal the history of the solar system's formation. Understanding what comets are made of means understanding some of the most pristine, unchanged matter left over from the birth of our planetary system billions of years ago. The core of every comet is its nucleus, a solid chunk of ice and rock that can range from a few hundred meters to tens of kilometers across. In 1950, astronomer Fred Whipple proposed what became known as the dirty snowball model of comets, suggesting that comet nuclei were mixtures of ice and dust. This model has proven remarkably accurate, though modern observations have revealed that comets might be better described as icy dirt balls. They contain more rock and dust than Whipple initially thought, sometimes with dust making up 50% or more of their mass. The ice in a comet is primarily water ice, frozen solid at the incredibly cold temperatures found in the outer solar system. But comets contain more than just frozen water. They also harbour other volatile compounds, substances that evaporate at relatively low temperatures. Carbon monoxide ice exists in comet nuclei, freezing at temperatures even lower than water. Carbon dioxide, frozen into dry ice, is abundant in many comets. Methane, ammonia, formaldehyde, methanol, and hydrogen cyanide have all been detected in comets, creating a chemical inventory that reads like an exotic mixture of the simplest molecules that carbon, nitrogen, and oxygen can form when combined with hydrogen. These volatile compounds exist as ices throughout the comet's interior when it's far from the Sun, creating a porous, fluffy structure rather like hard frozen snow. The density of comet nuclei is remarkably low, typically less than water, around 0.6 grams per cubic centimetre. This low density reveals that comets are not solid blocks of ice, but rather loosely consolidated collections of icy particles with substantial void space between them. Picture a pile of snowballs loosely stuck together rather than a single solid block of ice, and you have a reasonable mental image of a comet's internal structure. Mixed throughout this icy matrix are dust particles, tiny grains of rock and organic material. These dust grains are incredibly small, typically measured in micrometers, smaller than the width of a human hair. They're composed of silicates similar to the minerals found in Earth's rocks, compounds of silicon and oxygen mixed with elements like magnesium and iron. Some grains are pure carbon, forming soot-like particles. Others are complex mixtures of organic molecules, carbon-based compounds that include some of the building blocks of life. The organic material in comets is particularly fascinating. When spacecraft have analysed comets up close, or when laboratories have examined samples collected from comet tails, they've found complex organic molecules, including amino acids, the building blocks of proteins, and nucleobases, components of DNA and RNA. These molecules don't indicate that comets harbour life, but they demonstrate that the chemical precursors necessary for life can form naturally in space and were present in the early solar system. Some scientists have proposed that comets bombarding the early Earth might have delivered substantial quantities of organic molecules and water, potentially contributing to the origins of life on our planet. The European Space Agency's Rosetta mission, which orbited and studied Comet 67P/Churyumov-Gerasimenko from 2014 to 2016, provided unprecedented detail about comet composition. The Philae lander, which touched down on the comet's surface, detected 16 organic compounds as the comet's warmth released them from the ice. Among these were 4 compounds never before detected on a comet, including molecules that can act as precursors to amino acids. The comet's surface appeared darker than coal, with a reflectivity of only about 6%, due to the dark organic compounds mixed with the ice. When a comet approaches the Sun, solar heating begins to affect its structure. At distances beyond about 5 astronomical units, 5 times the Earth-Sun distance, roughly Jupiter's orbit, a comet remains frozen and inert. But as it moves closer, sunlight warms the surface. The most volatile ices, like carbon monoxide and carbon dioxide, begin to sublimate, transforming directly from solid to gas without passing through a liquid phase. This sublimation creates pressure beneath the surface, and when that pressure becomes strong enough, gas bursts through the surface, carrying dust particles along with it. These jets of gas and dust create the coma, the glowing atmosphere that surrounds the nucleus and makes the comet visible from Earth. The coma can grow to enormous sizes, sometimes exceeding the diameter of Jupiter, even though the nucleus producing it might be only a few kilometers across. The gas molecules in the coma, particularly water vapor, are broken apart by solar ultraviolet radiation, creating a complex chemistry. Hydroxyl radicals, hydrogen atoms, oxygen atoms, and other fragments fluoresce in sunlight, emitting light at specific wavelengths that give the coma its greenish or bluish tint. The dust released from the comet creates a dust tail, pushed away from the Sun by radiation pressure, the physical push that photons exert when they strike and reflect off particles. This dust tail typically appears yellowish-white because it's sunlight reflecting off dust particles. The tail can extend for millions of miles, creating the spectacular displays visible from Earth. A separate ion tail, composed of ionized gas molecules, is pushed by the solar wind rather than radiation pressure. The ion tail glows with its own light as the ionized molecules fluoresce, often appearing blue due to emissions from ionized carbon monoxide. This ion tail points directly away from the Sun, shaped by the magnetic fields carried in the solar wind. The nucleus itself undergoes changes as the comet repeatedly approaches the Sun. Each passage evaporates a layer of ice from the surface, typically removing a few meters of material per orbit for comets that pass close to the Sun. As the ice sublimates, some dust particles escape with the gas, but others fall back to the surface, gradually building up a layer of dust and larger rock fragments. Over many orbits, this can create a crust of non-volatile material covering the underlying ice, insulating it from solar heating. Some old comets develop such thick crusts that they become inactive, no longer producing visible comas or tails, even when they approach the Sun. NASA's Deep Impact mission in 2005 deliberately crashed a copper impactor into Comet Tempel 1 to excavate beneath the surface and observe the fresh material. The impact created a crater and ejected plumes of material that spectroscopic analysis revealed to be rich in water ice mixed with organic compounds and fine dust. The material beneath the surface appeared similar to, but slightly richer in ice than the surface material, confirming that the interior retains more pristine composition while the surface becomes processed by solar heating. The ratio of different isotopes in comet materials provides clues about where and when they formed. Deuterium, a heavy isotope of hydrogen with an extra neutron, exists in different ratios to normal hydrogen depending on the temperature at which water formed. Measurements of the deuterium to hydrogen ratio in various comets have shown considerable variation, suggesting that comets formed in different regions of the early solar system or at different times. Some comets have deuterium ratios similar to Earth's oceans, while others differ substantially, helping scientists understand whether comets could have delivered Earth's water. The dust particles in comets are themselves diverse and complex. Some grains are crystalline, showing that they formed at high temperatures, possibly near the young Sun, then were transported outward and incorporated into comets forming in the cold outer solar system. Other grains are amorphous, formed at low temperatures in the outer reaches. This mixture indicates that the solar nebula was not a static, orderly system, but rather a dynamic environment with extensive mixing, where materials formed in the hot inner regions could be transported outward, and vice versa. Comets also contain tiny pre-solar grains, particles that formed around other stars before the Sun existed and survived incorporation into our solar system. These grains have isotopic compositions distinctly different from solar system materials, marking them as true interstellar visitors preserved within comets. They're typically only nanometers to micrometers in size, but they're extraordinarily valuable because they provide samples of stars that lived and died before our solar system formed, preserved in these frozen time capsules. When comets break apart, as they sometimes do when tidal forces or internal pressure cause the nucleus to fragment, the exposed interior shows the layered structure built up over billions of years. Some regions are richer in ice, others in dust. Some layers contain different mixtures of volatile compounds. These variations likely reflect changes in conditions in the solar nebula as the comet grew by accumulation, recording the changing composition of material in the comet-forming region over time. The darkening of comet surfaces producing the surprisingly low reflectivity observed by Rosetta and other missions results from the organic compounds being altered by solar radiation and cosmic rays. This radiation processing, called space weathering, gradually darkens and reddens the surface materials over time. The very dark surfaces of comet nuclei tell us they've been exposed to space for long periods, accumulating radiation damage that has transformed the original icy material into a darker, more complex mixture. Comets are messengers from the outer solar system, preserving materials that have remained largely unchanged for over 4 billion years. While planets have been geologically active, melting and reforming their materials countless times, and asteroids have been heated and altered, comets have remained frozen in the deep cold of the outer solar system, maintaining their original composition. They're samples of the primordial solar nebula, the disk of gas and dust from which the planets formed, carrying within their icy matrices the water, organic molecules, and mineral grains that were present at the dawn of the planetary system, offering glimpses into the raw materials from which everything in our solar system, including Earth and ultimately life itself, was constructed. The incredible density of neutron stars. Imagine taking the entire mass of our Sun, a sphere so large that over 1 million Earths could fit inside it, and compressing it down to the size of a city. Not a large metropolitan area, sprawling across thousands of square miles, but just the central core, perhaps 12 or 15 miles across. This is a neutron star, an object so dense that a single teaspoonful of its material would weigh about 1 billion tons on Earth. To put that in perspective, that single teaspoon would weigh more than all the cars, trucks and buildings in a major city combined. This density is so extreme that it represents a fundamentally different state of matter, one that can only exist under the most extraordinary conditions in the universe. Neutron stars are born in the violent death throes of massive stars. When a star much larger than our Sun, typically at least 8 times more massive, exhausts the nuclear fuel in its core, it can no longer generate the heat and pressure needed to support itself against its own gravity. The core collapses catastrophically in less than a second, falling inward at speeds approaching 1/4 of the speed of light. The outer layers of the star, rebounding from this collapse, are blown away in a supernova explosion that briefly outshines an entire galaxy. What remains at the center, crushed under its own gravity to densities that boggle the mind, is a neutron star. To understand how neutron stars achieve such incredible density, you need to understand what happens to matter under extreme compression. In normal matter, atoms are mostly empty space. The nucleus of an atom containing protons and neutrons occupies only a tiny fraction of the atom's volume. The rest is empty space with a few electrons orbiting at relatively vast distances. In a solid object, like a piece of iron or a rock, the atoms are packed as closely together as the electromagnetic forces between them allow, but there's still enormous amounts of empty space within each atom. As you compress matter to higher and higher densities, you eventually overcome the forces that keep atoms intact. The electrons are stripped away from their nuclei, creating a plasma of free electrons and atomic nuclei. Compress further, and the electrons themselves are forced to occupy higher and higher energy states due to quantum mechanical principles. Eventually, at densities found in white dwarf stars, electron degeneracy pressure provides the support against gravity. The electrons can't be compressed any further without violating the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. But if you compress matter beyond even this point, as happens in the core collapse of a massive star, something remarkable occurs. The electrons are forced so close to the protons in atomic nuclei that they combine through a process called electron capture. A proton and an electron merge to form a neutron, releasing a neutrino in the process. This happens not just occasionally, but to nearly every proton in the collapsing core. Within a fraction of a second, the matter that was once composed of atoms, with protons, neutrons and electrons maintaining their separate identities, transforms into a sea of neutrons, packed together so tightly that they're essentially touching. The neutrons themselves now provide the pressure that supports the star against further collapse. Just like electrons, neutrons obey the Pauli exclusion principle and cannot be compressed indefinitely. This neutron degeneracy pressure halts the collapse, but only after the matter has been compressed to densities comparable to that of an atomic nucleus. In fact, you can think of a neutron star as essentially a single gigantic atomic nucleus, several kilometers across, containing more neutrons than there are atoms in all the planets of our solar system combined. The density at the center of a neutron star is estimated to be around 500 million to perhaps a billion tons per cubic centimeter. At these densities, a cubic centimeter, about the size of a sugar cube, would contain more mass than Mount Everest. The entire mass of humanity, every person on Earth, could be compressed into a volume smaller than a grain of sand at neutron star densities. These numbers are so far beyond everyday experience that they almost lose meaning, but they represent real physical conditions that exist in these objects. The structure of a neutron star is complex and layered. At the surface, there's a thin atmosphere only a few centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, where matter exists in a crystalline lattice. Here, atomic nuclei, now incredibly neutron-rich and unlike any nuclei found on Earth, are arranged in a solid structure with a sea of electrons moving between them. This crust is extraordinarily rigid. It's been calculated that the material of a neutron star's crust is about 10 billion times stronger than steel. Deeper into the neutron star, at densities about 1,000,000 times that of normal atomic nuclei, the inner crust begins. Here, neutrons start to leak out of the nuclei and form a superfluid that exists between and around the nuclei. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever. This neutron superfluid can exhibit bizarre quantum mechanical behavior on a macroscopic scale. Below the crust lies the outer core, where the density becomes so high that nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain charge neutrality. The neutrons in this region form a superfluid, while the protons form a superconductor, a state where electrical current can flow without resistance. These quantum fluids make up the bulk of the neutron star's interior. At the very center, in the inner core, conditions become so extreme that we're not entirely certain what happens. The density may exceed that of atomic nuclei by a factor of several times. At these densities, neutrons themselves might break down into their constituent quarks, creating what's called a quark-gluon plasma, or strange quark matter. Alternatively, other exotic particles predicted by physics but never observed might appear. The center of a neutron star is one of the few places in the universe where matter exists in states that can't be recreated or studied in laboratories on Earth. The incredible density of neutron stars creates gravitational fields so strong that they noticeably warp space-time. At the surface of a neutron star, gravity is about 200 billion times stronger than on Earth. If you could somehow stand on a neutron star's surface, though you would instantly be crushed and vaporized, you would weigh 200 billion times more than you do on Earth. A fall from even a tiny height of 1 centimeter would be fatal, as you would hit the surface at a significant fraction of the speed of light. This intense gravity affects light itself. Photons climbing out of a neutron star's gravitational well lose energy through gravitational redshift. Light that starts as high-energy X-rays at the surface might emerge as lower-energy radiation by the time it escapes into space. The gravity also bends light rays, causing light from the far side of the neutron star to curve around and become visible to an observer. This means you could potentially see more than half of the neutron star's surface at once, as light from behind the star bends around it to reach your eyes. The intense gravity also means that space and time are severely warped near a neutron star. Clocks at the surface of a neutron star run about 30% slower than clocks far away in flat space-time. This time dilation is a real physical effect. Processes genuinely occur more slowly in the strong gravitational field at the surface compared to regions far from the star. The rotation of neutron stars adds another layer of extremes to their already extreme nature. Many neutron stars spin rapidly, some completing hundreds of rotations per second. This happens because of conservation of angular momentum. When the core of the parent star collapses, any rotation it had is amplified enormously as the radius shrinks. Just as a figure skater spins faster when pulling their arms in, a collapsing stellar core spins faster as it shrinks. The result can be a neutron star spinning so fast that its equator is moving at a significant fraction of the speed of light. The fastest spinning neutron star known rotates 716 times per second. Imagine an object with more mass than the Sun, compressed to the size of a city, spinning around more than 700 times every second. The surface at the equator of this neutron star is moving at about 24% of the speed of light. At these rotation rates, centrifugal forces become significant, causing the neutron star to bulge at the equator and flatten at the poles. Yet even with this rapid rotation and the outward force it creates, the neutron star holds together, a testament to the incredible strength of neutron degenerate matter and the overwhelming power of its gravity. The magnetic fields of neutron stars are among the strongest in the universe. The collapse that forms a neutron star compresses and amplifies any magnetic field present in the parent star's core. The result can be magnetic fields 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields even stronger, up to 1,000 times more intense still. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms stretched by these fields become elongated, many times longer than they are wide, fundamentally changing their properties. These magnetic fields, combined with rapid rotation, power some of the most energetic phenomena in the universe. Charged particles, accelerated along magnetic field lines, emit beams of radiation from the magnetic poles. If these beams sweep across Earth as the neutron star rotates, we detect regular pulses of radiation, which is why many neutron stars are called pulsars. The precision of these pulses rivals that of atomic clocks, with some pulsars maintaining their timing to within microseconds over years or decades. The density of neutron stars also means that they have very deep gravitational wells. The escape velocity from the surface of a typical neutron star is about 150,000 kilometers per second, roughly half the speed of light. This means that matter falling onto a neutron star from a companion star in a binary system releases tremendous amounts of energy. The infalling material accelerates to these extreme velocities and slams into the surface with incredible force, heating to temperatures of hundreds of millions of degrees and emitting intense X-rays and gamma rays. Neutron stars can also collide with each other in binary systems where two neutron stars spiral together due to the emission of gravitational waves. When they finally merge, the collision creates conditions even more extreme than those in individual neutron stars. The merger produces a burst of gravitational waves that ripple through space-time, along with electromagnetic radiation across the spectrum. These collisions are thought to be the primary source of heavy elements like gold and platinum in the universe, forged in the incredibly dense, hot material ejected during the merger. The study of neutron stars provides a unique laboratory for physics under extreme conditions. The densities, magnetic fields, rotation rates, and gravitational fields found in and around neutron stars simply don't exist anywhere else that we can observe. By studying these objects, physicists can test theories about how matter behaves at nuclear densities, how gravity warps spacetime in strong field regimes, and how quantum mechanics manifests on macroscopic scales. Every observation of a neutron star, every measurement of its mass, radius, rotation, or cooling rate provides constraints on fundamental physics that cannot be obtained any other way, offering glimpses into realms of matter and energy that push the very boundaries of our understanding. What alien civilizations might actually look like? When most people imagine alien civilizations, they picture humanoid beings with large heads, sleonder bodies, and advanced technology that allows them to cross the vast distances between stars. Science fiction has given us countless variations: green-skinned Martians, insectoid hive minds, crystalline energy beings, peaceful explorers, and hostile invaders alike. But what would alien civilizations actually look like if we base our expectations on biology, physics, chemistry, and evolutionary principles rather than imagination alone? The answer reveals possibilities both familiar and utterly strange, shaped by the same fundamental laws that govern life on Earth, but expressed through the infinite variations that different worlds and evolutionary histories would create. The foundation of any alien civilization begins with evolution. On Earth, every organism exists because its ancestors survived and reproduced more successfully than competitors. Natural selection shaped everything from bacterial flagella to human brains, optimizing organisms for their specific environments and challenges. The same process would operate on any world where life exists. Alien organisms would be shaped by their planet's gravity, atmosphere, temperature, available nutrients, predators, and countless other factors operating over millions or billions of years. Evolution is relentless, creative, and opportunistic, finding solutions to survival challenges through whatever mechanisms work. Gravity would profoundly influence alien body structures. On a high-gravity planet, perhaps 1.5 times Earth's gravity, organisms would need stronger skeletal structures to support their weight. Animals might evolve shorter, stockier bodies with thicker bones and more powerful muscles. Tall, slender forms would be disadvantageous because they would require too much structural support and energy to maintain. Intelligent beings on such a world might stand only 3 or 4 feet tall despite being as massive as humans, with powerful legs and low centers of gravity to move efficiently under the stronger gravitational pull. On a low-gravity planet, the opposite constraints would apply. With less gravitational force to overcome, organisms could grow taller and more delicate. Bones could be lighter and more slender. Flying might be easier, allowing evolution to produce larger flying organisms than Earth's giant pterosaurs. Intelligent beings might stand 8 or 10 feet tall with elongated limbs, moving with a grace that would seem almost balletic to Earth-based observers. Their skeletal structure might resemble bird bones, hollow and reinforced with internal struts rather than solid like mammalian bones. The atmospheric composition would shape how aliens breathe and what biochemistry they use. On Earth, most complex life uses oxygen for metabolism because burning fuel with oxygen releases large amounts of energy efficiently. But oxygen was not always abundant. Early Earth had an atmosphere dominated by nitrogen, carbon dioxide, methane, and other gases. The oxygen we breathe today came from photosynthetic bacteria that gradually transformed the atmosphere over billions of years in what's called the Great Oxidation Event. An alien planet might never undergo such a transformation, leaving its atmosphere oxygen poor. Life there might use different metabolic pathways, perhaps based on sulfur compounds, hydrogen, or methane. The type of star a planet orbits would influence alien vision and perhaps their entire sensory experience of reality. Our sun emits most strongly in visible light wavelengths, the colours we can see, and Earth's organisms evolved eyes sensitive to these wavelengths because that's where the most light was available. But a planet orbiting a red dwarf star would receive most of its light in infrared wavelengths. Organisms evolving there might develop eyes sensitive to infrared rather than visible light. To them, what we call visible light might be invisible ultraviolet, and their daylight would be our infrared. An alien from such a world would perceive colours and see objects in ways completely foreign to human experience. Conversely, a planet orbiting a hotter, bluer star would receive more ultraviolet light. Evolution might produce eyes sensitive to ultraviolet wavelengths, allowing these aliens to see patterns and colours invisible to humans. Many Earth organisms, including bees and some birds, can already see into the ultraviolet range, perceiving patterns on flowers and plumage that humans cannot detect without special cameras. An alien species with full ultraviolet vision would experience a visual world enriched with information and beauty we cannot access. Communication methods would evolve based on environmental constraints and available sensory channels. On Earth, humans primarily communicate through sound, speaking and hearing, supplemented by visual cues like facial expressions and gestures. But sound travels poorly in thin atmospheres and not at all in vacuum. An alien species on a world with a thin atmosphere might rely more heavily on visual communication, colour changes, bioluminescent patterns, or elaborate gestural languages. Octopuses on Earth already use colour-changing skin cells, called chromatophores, to communicate, creating flowing patterns across their bodies. An intelligent species with similar abilities might communicate through rapidly shifting colour displays, conveying complex ideas through patterns that flow across their skin in what would appear to us as living art. Some aliens might communicate through vibrations transmitted through the ground or through their planet's oceans. Whales and elephants on Earth use low-frequency sounds that travel great distances. Elephant calls can travel several miles through the ground. An intelligent species might evolve specialized organs for creating and detecting vibrations, communicating through seismic signals that travel through rock or sediment. Their language would be invisible and inaudible to humans without special equipment to detect the vibrations. Chemical communication, already used extensively by Earth's insects through pheromones, might become the primary communication method for some species. Aliens might communicate through releasing complex mixtures of chemicals that other members of their species detect through sensitive chemoreceptors. Their language would consist of scents and tastes with grammar and syntax encoded in the ratios and combinations of different molecules. To humans, their most profound poetry and scientific papers would be nothing more than smells. Body structure would reflect evolutionary history and environmental pressures. The bilateral symmetry seen in most Earth animals, a left side mirroring a right side, emerged early in evolution and became locked in. But aliens might evolve radial symmetry like starfish, with body parts arranged around a central axis. An intelligent being with radial symmetry might have arms, eyes, and sensory organs distributed evenly around their body, giving them a 360-degree field of awareness with no natural front or back. Their psychology and culture might be profoundly affected by experiencing the world without a preferred direction of travel or attention. The number of limbs is not fixed by any physical law. Earth's vertebrates settled on 4 limbs relatively early in evolutionary history, but arthropods, insects, spiders, crustaceans have 6, 8, or even dozens of legs. An alien species might evolve with 3 limbs arranged in a triangle, giving them stable tripod support at all times. They might have 6 limbs, 4 for walking and 2 manipulator arms. Or they might have dozens of tentacles like an octopus, each capable of independent complex movement and manipulation. Their tool use and technology would develop along entirely different lines than human technology, shaped by their different manipulative abilities. Intelligence itself might manifest in forms unlike human intelligence. Human intelligence is highly centralized. Most of our cognitive processing occurs in our brain, a single organ in our head. But octopuses, among Earth's most intelligent invertebrates, have a distributed nervous system with neurons throughout their arms that can make independent decisions. An alien species might have multiple brain centers distributed throughout their body, or they might have a collective intelligence where individual organisms are relatively simple, but groups display emergent intelligence through their interactions, similar to how ant colonies solve complex problems that individual ants cannot. Social structure would influence civilization development. Humans are intensely social primates who naturally form groups, cooperate, compete, and create complex hierarchies. An intelligent species that evolved from solitary predators might have very different social instincts, perhaps coming together only to mate and raise young, then separating again. Their civilization would be built by individuals who value isolation and independence over community and cooperation. Or aliens might be eusocial, like bees or ants, with specialized castes, workers, soldiers, reproducers, genetically programmed for different roles. Their civilization might function as a superorganism where individual identity barely exists. Lifespan would profoundly affect culture and technology development. If an alien species naturally lives for thousands of years, they might approach problems with a patience humans cannot fathom, willing to spend centuries on single projects. Their sense of urgency and change would operate on timescales that would frustrate any human trying to interact with them. Conversely, a species with lifespans of only a few years might compress their entire cultural and technological development into periods that humans would find incomprehensibly rapid. Environmental factors would shape not just biology, but psychology and culture. A species that evolved in oceans might think about space and boundaries very differently than land-dwelling humans. Without solid ground beneath them, without permanent structures that last for generations, their concepts of property, territory, and permanence might be fluid in ways humans struggle to understand. A species that evolved in dense forests with limited sightlines might have very different concepts of distance and perspective than humans who evolved in open savannas, where seeing for miles was possible and valuable. Technology would develop based on available resources and environmental challenges. A civilization on a water world with no dry land would never discover fire, fundamentally altering their technological development pathway. Without fire, they couldn't easily work metals, make pottery, or develop steam power. Their technology might focus on biological engineering, breeding organisms to serve specific functions, or on working with materials that don't require heat processing. They might develop advanced understanding of hydrodynamics, pressure, and acoustic phenomena, while lacking technologies that humans developed early. A civilization on a planet with extreme temperature swings might prioritize insulation and environmental control. A species on a tidally locked planet with one side in permanent daylight and the other in eternal darkness might build their civilization in the twilight zone between extremes. Or they might develop two separate cultures adapted to the radically different environments. Their technology would need to handle these extremes, perhaps leading to advanced materials science long before other fields developed. Reproduction methods would influence family structures and social organization. If aliens reproduce through spawning like fish, releasing eggs and sperm into water where fertilization occurs externally, they might have no concept of nuclear family or parental bonds. Eggs might be raised communally or even left to develop independently. If reproduction requires 3 or more sexes simultaneously, their social structures and mating rituals would be incomprehensibly complex to humans. If they reproduce through budding or fission, creating genetic copies of themselves, their concepts of individuality and identity might be fundamentally different from species that reproduce sexually and value genetic diversity. Sensory experiences beyond human comprehension might exist. Some Earth organisms detect magnetic fields, electric fields, pressure changes, or polarized light, senses humans lack entirely. An alien species might perceive reality through senses we don't possess and cannot easily imagine. They might see the world through echolocation like bats, building a sonic map of their environment. They might sense electrical fields like sharks detecting the bioelectric signatures of other organisms. They might perceive time differently, with reaction times much faster or slower than humans, making their subjective experience of duration incompatible with ours. The Fermi paradox asks why, if alien civilizations are likely to exist, we haven't detected them yet. One possible answer is that we're looking for the wrong things. We search for radio signals because that's how we communicate, and we look for visible structures, like cities, because that's how we build. But an alien civilization might never develop radio technology, using entirely different communication methods. They might build in ways that leave no visible trace from space. They might exist on entirely different timescales, civilizations that rise and fall in centuries, while humans are still learning to farm, or civilizations that operate so slowly that their entire recorded history spans less time than a human lifetime. If contact ever occurs between human and alien civilizations, the challenges would be immense. Even if both species are trying to communicate, fundamental differences in sensory experience, cognition, timescales, and conceptual frameworks might make mutual understanding nearly impossible. Imagine trying to explain color to someone born blind, or music to someone born deaf, or love to a species that doesn't experience emotions. Now multiply those challenges by every aspect of existence: time, space, causation, identity, purpose. Communication might require generations of effort and specialized translation technologies we haven't yet imagined. What alien civilizations might actually look like encompasses possibilities ranging from vaguely familiar, carbon-based organisms breathing oxygen on Earth-like worlds shaped by convergent evolution into forms somewhat similar to Earth's creatures, to utterly incomprehensible beings whose very existence challenges our definitions of life, intelligence, and civilization. They might be silicon-based entities living in molten rock at temperatures that would vaporize Earth's organisms. They might be electromagnetic patterns in planetary magnetic fields, or chemical reaction networks in liquid methane seas, or quantum coherence patterns in neutron star crusts. The universe is vast and ancient, and if intelligence has emerged elsewhere, it has had billions of years and countless different environments in which to develop into forms limited only by physics, chemistry, and the creative power of evolution operating across deep time on worlds we've never seen. The thick atmospheres of Jupiter and Saturn. Jupiter and Saturn are fundamentally different from the rocky planets of the inner solar system. They have no solid surface to stand on, no ground beneath the sky. Instead, these gas giants are essentially enormous atmospheres all the way down, layers upon layers of gas that gradually transition from thin upper hazes to dense, crushing depths, where pressure transforms hydrogen into states of matter that don't exist naturally anywhere on Earth. Understanding these thick atmospheres means understanding worlds where the atmosphere isn't just a thin shell surrounding a planet, it is the planet. The atmospheres of Jupiter and Saturn are composed primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. Jupiter's atmosphere is about 90% hydrogen and 10% helium by number of molecules, with trace amounts of methane, ammonia, water vapor, and other compounds making up less than 1%. Saturn has a similar composition, though with slightly less helium, about 96% hydrogen and 3% helium, with the missing helium thought to have settled deeper into the planet's interior over billions of years. This composition mirrors the composition of the Sun and the primordial solar nebula from which the planets formed, marking these giants as worlds that captured and retained their original atmospheres from the planet-forming disk. The visible clouds we see when we look at Jupiter and Saturn exist in the uppermost layers of these atmospheres, in a region where temperatures and pressures allow various compounds to condense into droplets and crystals. On Jupiter, the highest cloud layer consists of ammonia ice crystals forming at temperatures around -150 degrees Celsius, where ammonia gas freezes into white ice. These ammonia clouds give Jupiter's zones, the bright bands that circle the planet, their brilliant white appearance. Below this ammonia layer, at slightly higher temperatures and pressures, ammonium hydrosulfide forms another cloud deck, creating brown and tan colours. Deeper still, water ice and liquid water droplets form clouds, though these are rarely visible from above, hidden beneath the overlying layers. Saturn's cloud structure is similar but more subdued. The planet appears more uniformly golden tan because a high-altitude haze of unknown composition partially obscures the underlying cloud layers. This haze may consist of complex organic molecules called tholins, created when ultraviolet light from the Sun breaks apart methane molecules in the upper atmosphere, allowing the fragments to recombine into larger, more complex hydrocarbons. These organic hazes absorb blue light and scatter red and yellow light, giving Saturn its characteristic buttery colour. The temperatures in these atmospheres change dramatically with depth. At the cloud tops, where pressure is similar to Earth's atmospheric pressure at sea level, temperatures on Jupiter hover around -145 degrees Celsius. On Saturn, they're even colder, around -180 degrees Celsius, because Saturn is nearly twice as far from the Sun and receives less solar heating. But as you descend into these atmospheres, temperatures rise rapidly. The increase comes partly from the Sun's heat that has been absorbed and transported downward, but more significantly from the planet's internal heat. Both Jupiter and Saturn emit more energy than they receive from the Sun. Jupiter radiates about 1.7 times as much energy as it absorbs from sunlight, while Saturn radiates about 1.8 times as much. This extra energy comes from the planet's interiors. Jupiter is still slowly contracting under its own gravity, a process that converts gravitational potential energy into heat through a mechanism called Kelvin-Helmholtz contraction, named after the physicists Lord Kelvin and Hermann von Helmholtz, who described this process in the 19th century. Saturn has an additional heat source. Helium is slowly separating from hydrogen in its interior and sinking toward the centre, releasing gravitational energy as it falls. Much like rain falling through Earth's atmosphere releases energy. This internal heat drives powerful convection in the atmospheres. Warm gas rises from the depths, cools as it rises and expands, then sinks back down to be heated again. This convection creates enormous circulation cells that organize the atmospheres into the distinctive banded patterns visible on both planets. Rising gas forms the bright zones, where fresh ammonia ice crystals condense and create white clouds. Sinking gas forms the darker belts, where descending motion prevents cloud formation and allows us to see deeper into the atmosphere, where darker compounds and higher temperatures exist. The winds on Jupiter and Saturn are among the strongest in the solar system. Jupiter's equatorial region rotates faster than the rest of the planet, with winds reaching speeds of about 360 kilometers per hour, roughly 225 miles per hour. Saturn's equatorial winds are even more extreme, racing along at up to 1,800 kilometers per hour, over 1,100 miles per hour, making them the fastest planetary winds in the solar system. These winds are organized into jet streams, narrow bands of fast-flowing gas that separate the zones and belts. The jet streams are remarkably stable, maintaining their positions and speeds for decades or longer. The Great Red Spot on Jupiter is perhaps the most famous atmospheric feature in the solar system. This enormous storm, large enough to swallow 2 or 3 Earths, has been observed continuously since at least 1830, and possibly as far back as the 1660s, when early telescope observers noted a large spot on Jupiter. The storm is an anticyclone, rotating counterclockwise in Jupiter's southern hemisphere, with winds at its edges reaching 400 kilometers per hour. The storm's longevity remains somewhat mysterious. On Earth, hurricanes dissipate within days or weeks when they move over land or cooler water, but the Great Red Spot has persisted for centuries. Its stability likely comes from the fact that Jupiter has no solid surface to create friction and slow the winds, and the storm may draw energy from the smaller storms it absorbs, and from the temperature difference between the warm interior and cold upper atmosphere. Saturn hosts similar, but generally smaller and shorter-lived storms. Approximately once per Saturnian year, about every 30 Earth years, a massive storm erupts in Saturn's northern hemisphere, growing to encircle the entire planet before eventually dissipating. These great white spots, as they're called, were observed in 1876, 1903, 1933, 1960, 1990, and 2010, following a remarkably regular pattern tied to Saturn's seasons. The storms appear to originate when seasonal heating destabilizes the atmosphere, allowing deep, moist convection to punch through the stable layers above and create violent thunderstorms. Lightning occurs on both Jupiter and Saturn, detected by the Voyager, Galileo, and Cassini spacecraft through radio emissions, and in some cases visible flashes. The lightning on these worlds is similar to terrestrial lightning, electrical discharges between regions of different charge within clouds, but can be far more powerful than Earth's lightning. Individual lightning bolts on Saturn have been measured at up to 1 million times more powerful than typical lightning on Earth. These storms occur in the water cloud layer, where the same process that creates thunderstorms on Earth, rising moist air forming clouds and separating electrical charges, operates on these giant planets. As you descend deeper into these atmospheres, the pressure increases relentlessly. At depths of a few hundred kilometers below the cloud tops, pressures reach thousands of times Earth's atmospheric pressure, and temperatures climb to hundreds of degrees Celsius. The atmosphere becomes denser and denser, transitioning gradually from gas to liquid, though there's no sharp boundary, no ocean surface where you suddenly plunge from air into water. Instead, the hydrogen and helium gradually become so compressed that they take on liquid properties, while still being hot enough that calling them liquid doesn't quite capture their state. They exist in a supercritical fluid state, where the distinction between gas and liquid breaks down. Descend even deeper, to depths of 10,000 to 20,000 kilometers, and pressures reach millions of times Earth's atmospheric pressure. Under these extreme conditions, hydrogen transforms into metallic hydrogen, a state of matter where the atoms are squeezed so tightly that their electrons are freed from individual atoms and flow through the material like electrons in a metal. This metallic hydrogen is thought to make up the bulk of Jupiter's mass and a significant portion of Saturn's. It's an excellent electrical conductor, and the flow of metallic hydrogen in these regions, driven by the planet's rotation and internal convection, generates the powerful magnetic fields that both planets possess. The transition from molecular hydrogen to metallic hydrogen isn't abrupt. There's a gradual change over a range of depths where hydrogen takes on increasingly metallic properties. Scientists study this transition using laboratory experiments that compress hydrogen to extreme pressures and sophisticated computer simulations that model how atoms behave under conditions impossible to fully recreate on Earth. Understanding metallic hydrogen is crucial for understanding the interiors of Jupiter and Saturn, yet its properties remain uncertain because the pressures required, several million times atmospheric pressure, can only be achieved briefly in laboratory settings. At the very centres of Jupiter and Saturn may lie rocky cores, though whether these cores exist and how large they might be remains debated. Jupiter might have a core of rock and ice, containing 10 to 20 Earth masses, or it might have no distinct core at all, just a gradual increase in the concentration of heavy elements toward the centre. Saturn might have a similar core, though perhaps smaller relative to the planet's total mass. NASA's Juno mission to Jupiter and the Cassini mission's final orbits, diving between Saturn and its rings, have provided gravity measurements precise enough to constrain the planet's interior structures, revealing that both planets have somewhat diffuse cores rather than sharp boundaries between core and envelope. The scale of these atmospheres is almost incomprehensible. On Earth, the atmosphere extends perhaps 100 kilometers before space begins. On Jupiter and Saturn, the atmosphere extends downward for thousands upon thousands of kilometers, transitioning through states from thin gas to dense supercritical fluid to liquid metallic hydrogen. If you could somehow survive the crushing pressures and searing temperatures and descend through Jupiter's atmosphere, it would take days or weeks of continuous falling to reach the planet's center, passing through layer after layer of hydrogen in different states, all of it technically atmosphere, because there's no solid surface to mark where the atmosphere ends. The study of Jupiter's and Saturn's atmospheres extends beyond academic interest. Understanding how these atmospheres work, how convection organizes into bands, how storms form and persist, how energy is transported from the interior to space, helps scientists understand atmospheric dynamics more broadly. The principles governing Jupiter's atmosphere apply, with appropriate modifications, to Saturn's atmosphere, to the atmospheres of Uranus and Neptune, and even to the atmospheres of giant exoplanets orbiting other stars. Some exoplanets, called hot Jupiters, orbit extremely close to their stars and have atmospheres heated to thousands of degrees, creating extreme versions of the processes we observe on Jupiter and Saturn. These thick atmospheres also serve as laboratories for studying hydrogen under extreme conditions. Most of the normal matter in the universe is hydrogen, and understanding how it behaves under high pressure is crucial for understanding not just giant planets, but also brown dwarfs, objects intermediate in mass between planets and stars, and the interiors of low-mass stars. The hydrogen in Jupiter and Saturn exists across a range of pressures and temperatures that spans from Earth-like conditions in the upper atmosphere to conditions approaching those in stellar interiors in the metallic hydrogen regions, providing natural experiments that inform our understanding of matter itself across a vast range of conditions. The lighthouse stars that spin incredibly fast. In 1967, a graduate student named Jocelyn Bell noticed something peculiar in her radio telescope delta, a signal that pulsed with extraordinary regularity, repeating every 1.3373 seconds. The precision was so remarkable that she and her advisor initially wondered whether they had detected an artificial signal from an extraterrestrial civilization. They jokingly called it LGM-1 for Little Green Men. But as more of these pulsing sources were discovered, each with its own precise period, it became clear they were witnessing something natural, but entirely unexpected. Rapidly spinning neutron stars whose beams of radiation sweep across Earth like cosmic lighthouses. These objects, now called pulsars, are among the most extreme objects in the universe. They are neutron stars, the collapsed cores of massive stars that exploded as supernova, compressed to densities where a sugar cube-sized amount of material would weigh as much as a mountain. What makes pulsars special is not just their incredible density, but their rotation. These stars spin at rates that seem impossible for something so massive. Many complete one rotation in less than a second, some in mere milliseconds, whirling around hundreds of times per second while containing more mass than the Sun. The story of a pulsar begins with the death of a massive star. When a star, at least 8 times more massive than the Sun, exhausts its nuclear fuel, its core collapses catastrophically. The outer layers rebound and explode outward as a supernova, but the core continues collapsing until nuclear forces halt the compression, creating a neutron star about 12 miles across. This neutron star inherits the angular momentum of the original star's core, but because the radius has shrunk by a factor of perhaps 100,000, the rotation rate increases dramatically through conservation of angular momentum. Imagine a figure skater pulling their arms inward during a spin, rotating faster and faster as their radius decreases. The collapsing stellar core undergoes the same process, but on a far more extreme scale. A star that was rotating once every few weeks might produce a neutron star that rotates several times per second. The fastest spinning pulsar known, designated P-SRJ 1748-2446 AD, rotates 716 times per second. At its equator, the surface is moving at approximately 70,000 miles per second, nearly 1/4 the speed of light. At these speeds, the neutron star is ablate, bulging significantly at its equator due to centrifugal forces, yet it holds together through the tremendous strength of neutron degenerate matter and its own crushing gravity. The lighthouse effect that makes pulsars detectable comes from their magnetic fields. Neutron stars possess the strongest magnetic fields known in the universe, typically 1 trillion times stronger than Earth's magnetic field. When the core of the parent star collapses, any magnetic field present is compressed and amplified tremendously. This field doesn't simply shrink, it gets concentrated into a much smaller volume, intensifying to values that would tear apart atoms and polarize the vacuum of space itself. This intense magnetic field is not aligned with the neutron star's rotation axis. Just as Earth's magnetic poles don't coincide with its geographic poles, a neutron star's magnetic axis is typically tilted relative to its spin axis. Charged particles, primarily electrons and positrons, are accelerated along the magnetic field lines, particularly near the magnetic poles. These particles, accelerating at relativistic speeds, emit intense beams of radiation through a process called synchrotron radiation. The beams emerge from the magnetic poles, creating 2 searchlights that sweep through space as the neutron star rotates. When one of these beams sweeps across Earth, we detect a pulse of radio waves, X-rays, or gamma rays, depending on the pulsar's characteristics. The pulse arrives with extraordinary regularity. The best pulsars keep time as accurately as atomic clocks, varying by only microseconds over years. This precision exists because the neutron star is such a stable rotator. Its enormous rotational inertia, combined with its extreme density and rigidity, means that nothing can easily change its spin rate. It's like an enormous cosmic flywheel, storing vast amounts of rotational energy and releasing it only very gradually. The radio emission mechanism is complex and still not completely understood, despite decades of study. The acceleration of charged particles near the magnetic poles creates a cascade of electromagnetic radiation. These particles follow the curved magnetic field lines, and as they accelerate, they emit photons. These photons can interact with the intense magnetic field to create more particle-antiparticle pairs, which then accelerate and create more photons, building up a cascade that produces the intense radio emission we detect. The region where this occurs, just above the magnetic poles, is called the polar cap, and it's here that the lighthouse beams originate. Not all pulsars emit at the same wavelengths. Some are primarily radio pulsars, detected through their radio emission. Others are X-ray pulsars, emitting primarily high-energy X-rays. A few emit gamma rays, the most energetic form of electromagnetic radiation. Some pulsars emit across the entire electromagnetic spectrum simultaneously, creating pulses detectable from radio waves through gamma rays. The emission properties depend on factors like the neutron star's age, its magnetic field strength, its rotation rate, and the environment surrounding it. Young pulsars, recently formed in supernova explosions, tend to rotate faster and have stronger magnetic fields than old pulsars. The Crab pulsar, formed in a supernova observed by Chinese astronomers in 1054 AD, rotates 30 times per second and emits powerfully across the electromagnetic spectrum. It sits at the center of the Crab Nebula, the expanding remnant of that supernova explosion, and its intense radiation illuminates the surrounding nebula, causing it to glow. The pulsar acts like a cosmic power station, converting its rotational energy into electromagnetic radiation and high-energy particles that energize the nebula. Pulsars slow down over time, gradually losing rotational energy. This spin-down occurs because the rotating magnetic field acts like a brake. The magnetic field lines extend far into space, and as they rotate with the neutron star, they drag charged particles along, accelerating them and carrying away energy and angular momentum. This magnetic braking gradually robs the neutron star of its rotational energy. A young pulsar might slow down measurably over just a few years, while an old pulsar might take millions of years to show detectable changes in its period. The rate at which a pulsar slows down reveals information about its magnetic field strength and age. By measuring the current rotation period and the rate of change of that period, astronomers can estimate how long the pulsar has been spinning down and how much longer it will continue to pulse before its rotation becomes too slow and its magnetic field too weak to generate detectable radiation. Most pulsars have lifetimes of tens of millions of years as active radio sources before they fade from detectability, though the neutron star itself continues existing and spinning, just no longer producing observable pulses. Some pulsars experience sudden speed-ups, called glitches. The neutron star's rotation rate, which normally decreases steadily, suddenly increases slightly, then resumes its gradual slowdown. These glitches are thought to occur because the neutron star's interior contains a superfluid, a state of matter with zero viscosity that can flow without any resistance. This superfluid rotates faster than the star's crust, and occasionally, angular momentum transfers suddenly from the superfluid to the crust, causing the observable spin-up. Glitches provide rare windows into the exotic physics occurring inside neutron stars, where matter exists in states impossible to recreate in laboratories. Millisecond pulsars present a fascinating puzzle. These pulsars rotate hundreds of times per second, far faster than young pulsars, yet they're old neutron stars, billions of years old. How can an old pulsar be spinning so fast? The answer lies in a process called recycling. A millisecond pulsar was once a normal pulsar that slowed down over hundreds of millions of years. But if it's in a binary system with a companion star, and that companion evolves to become a giant star, matter can flow from the companion onto the neutron star. This infalling matter carries angular momentum, spinning up the neutron star like water hitting a water wheel. Over millions of years, the neutron star is spun up to millisecond periods, recycled into a new youth of rapid rotation. Some pulsars are part of binary systems where we can directly observe this process happening. X-ray binary pulsars show X-ray pulses as the neutron star accretes material from its companion. The infalling material, heated to millions of degrees before hitting the neutron star's surface, emits intense X-rays. These systems are the evolutionary precursors to millisecond pulsars, caught in the act of being spun up by accretion. The most rapidly rotating pulsars ever discovered are all millisecond pulsars, and some of them are in dense globular clusters where stars are packed closely together. The high stellar density in these clusters makes binary interactions more likely, creating environments where many neutron stars can be recycled through accretion. Some globular clusters contain dozens of millisecond pulsars, creating a cosmic percussion section where numerous neutron stars pulse at different rates, each one a precisely ticking clock with its own unique period. Pulsars can also have planets. The first exoplanets ever discovered orbit a pulsar called PSRB 1257+12. These planets were detected through tiny variations in the pulsar's timing. As the planets orbit, their gravity tugs the pulsar slightly back and forth, causing the pulses to arrive slightly early or late in a periodic pattern. The planets orbiting this pulsar are thought to be second-generation worlds, formed from the debris of the supernova explosion that created the neutron star, or possibly from material that later fell back onto the system. These are harsh worlds, bathed in intense radiation from the pulsar, utterly unlike the planets orbiting normal stars. Binary pulsars, where two neutron stars orbit each other, provide extraordinary laboratories for testing general relativity. The orbital motion of such systems produces gravitational waves that carry away energy, causing the orbit to shrink over time. The rate of orbital decay matches Einstein's predictions with incredible precision. The first binary pulsar discovered, PSRB 1913+16, provided the first indirect evidence for gravitational waves, decades before gravitational wave detectors directly observed them from merging black holes and neutron stars. The regularity of pulsar timing has practical applications. Astronomers use networks of millisecond pulsars across the galaxy as a cosmic timing array, watching for tiny correlated deviations in their pulse arrival times that would indicate gravitational waves passing through the galaxy. These pulsar timing arrays are sensitive to gravitational waves with much longer wavelengths than ground-based detectors can observe, potentially detecting the gravitational wave background from supermassive black hole mergers throughout the universe. Pulsars also serve as natural laboratories for extreme physics. The conditions near their surfaces, intense magnetic fields, extreme gravity, densities exceeding that of atomic nuclei, cannot be reproduced on Earth. By observing pulsars across the electromagnetic spectrum and measuring their properties precisely, physicists learn about how matter behaves under conditions that push the boundaries of our physical theories, testing general relativity in strong gravitational fields and probing the equation of state of matter at nuclear densities. These spinning neutron stars, these cosmic lighthouses flashing their beams across the universe, represent one endpoint of stellar evolution. From the violent collapse of a massive star's core emerges an object so dense, so rapidly spinning, so strongly magnetized that it challenges our understanding of physics. Each pulse detected from a pulsar is a message from one of the universe's most extreme environments, a precisely timed signal carrying information about physics at the edge of what's possible, reminding us that the universe contains objects and phenomena far stranger than we could have imagined before we discovered these remarkable, spinning stellar remnants. The glowing clouds, where stars are born. Scattered throughout the galaxy are vast clouds of gas and dust, some spanning hundreds of light years across, glowing with ethereal colours against the darkness of space. These nebulae are the cosmic nurseries, where stars come into being, regions where the raw materials of the universe, hydrogen and helium from the Big Bang, mixed with heavier elements forged in previous generations of stars, gather, collapse, and ignite into new points of light. Understanding these stellar nurseries means understanding one of the most fundamental processes in the cosmos, the transformation of diffuse gas into concentrated spheres of nuclear fusion that will shine for millions or billions of years. The process begins with the molecular cloud, a region of space where gas has accumulated and cooled to temperatures only a few degrees above absolute zero. These clouds are dark when viewed in visible light because the dust mixed with the gas blocks starlight from behind, creating dark patches against the background glow of the Milky Way. But observe them in infrared or radio wavelengths, and they reveal intricate structures, filaments, cores, and clumps where the density varies, creating a complex web of material threaded throughout these regions. Molecular clouds are mostly hydrogen, but at the low temperatures found within them, individual hydrogen atoms have paired up to form molecular hydrogen, H2. This molecular form is more stable at cold temperatures, and these clouds also contain molecules that might seem surprising in the depths of space: carbon monoxide, water, ammonia, formaldehyde, and even more complex organic molecules. The chemistry occurring in these cold clouds is rich and varied, with molecules forming on the surfaces of dust grains and in the gas phase, building up a diverse molecular inventory over millions of years. Something must disturb these clouds to initiate star formation. A cloud can exist in a stable state for a long time, with internal pressure from the gas supporting it against its own gravity. But if the cloud is compressed, if its density increases beyond a critical threshold, gravity begins to win. This compression can come from several sources: a shockwave from a nearby supernova explosion, pushing through space, the compression created when spiral arms of the galaxy pass through the region, or even the radiation and winds from existing massive stars that can trigger collapse in adjacent cloud material. Once collapse begins, the cloud fragments into smaller pieces. A single large molecular cloud doesn't collapse into one giant star. Instead, it breaks apart into hundreds or thousands of individual collapsing cores, each one potentially forming a star or a small system of stars. This fragmentation occurs because as the cloud collapses, it develops instabilities. Regions that are slightly denser collapse a bit faster, pulling in material from their surroundings, and these growing density enhancements become the seeds of individual stars. Picture one of these collapsing cores. Initially, it might be 1/10 of a light year across, containing perhaps a few times the mass of our Sun, with a density barely above that of the surrounding cloud. As it contracts under its own gravity, the material falls inward, but it doesn't fall uniformly. The core rotates slowly, inherited from the overall rotation of the cloud, and as it contracts, conservation of angular momentum causes it to spin faster, just as a figure skater spins faster when pulling their arms inward. This rotation prevents all the material from falling directly onto the forming star at the center. Instead, material settles into a rotating disk around the protostar, a flattened structure where gas and dust orbit the central condensation. This is a protoplanetary disk, the structure from which planets will eventually form. The material in this disk gradually spirals inward, losing angular momentum through viscosity and magnetic effects, feeding the growing protostar at the center, while the outer portions of the disk may remain in orbit for millions of years. As the protostar grows, accumulating more and more mass from the infalling material, its center heats up. Gravitational potential energy converts to thermal energy as material falls inward, and the temperature and pressure at the core climb steadily. The protostar begins to glow, first emitting infrared radiation, then gradually becoming brighter as it contracts. At this stage, it's not yet a true star. No nuclear fusion occurs at its core, but it's radiating energy produced by gravitational contraction, a process called Kelvin-Helmholtz contraction. The infalling material doesn't simply accumulate smoothly. Young protostars are violent, turbulent objects. They generate powerful magnetic fields that interact with the surrounding disk and the infalling gas. These magnetic fields can launch jets, narrow streams of gas that shoot outward from the poles of the protostar at speeds of hundreds of miles per second. These jets plow into the surrounding molecular cloud, creating bow shocks where they collide with the ambient gas, heating it and causing it to glow. These glowing regions, called Herbig-Haro objects, appear as bright knots and filaments near young stars, moving visibly over periods of years as the jets evolve and push through the surrounding gas. The jets serve an important function. They carry away angular momentum and energy, allowing material in the disk to continue falling onto the protostar. Without this mechanism to remove angular momentum, the disk would simply spin faster and faster, and accretion would halt. The protostar continues to accrete material and contract for hundreds of thousands to millions of years, depending on its mass. During this time, it's deeply embedded in the cloud that spawned it, hidden from view at visible wavelengths by the cocoon of gas and dust surrounding it. Infrared observations can penetrate this obscuration, revealing the glowing protostar and its disk within the dark cloud. These embedded protostars mark the earliest visible stages of star formation, objects that are still gaining mass and have not yet ignited nuclear fusion. Eventually, the temperature and pressure at the protostar's core reach a critical threshold, typically around 10 million degrees. At this point, protons begin to fuse, creating helium and releasing energy through nuclear fusion. The protostar becomes a true star, entering what's called the main sequence, where it will spend the majority of its life fusing hydrogen into helium. The energy released by fusion creates an outward pressure that finally halts the gravitational contraction, and the star settles into a stable configuration where gravity and pressure are balanced. When the star ignites, it begins to affect its surroundings dramatically. The radiation from the young star heats the surrounding gas and dust. Ultraviolet light from the star ionizes hydrogen atoms, stripping electrons away and creating a region of ionized gas called an H2 region. These ionized regions glow with a characteristic reddish-pink color, the result of electrons recombining with protons and cascading down through energy levels, emitting light at specific wavelengths. This is the glow we see in many famous nebulae: the Orion Nebula, the Eagle Nebula, the Lagoon Nebula, vast regions of ionized gas illuminated by the intense radiation from young hot stars. If the star is particularly massive and hot, more than about 8 times the Sun's mass, it produces copious ultraviolet radiation that can ionize gas over large volumes of space. A single massive star can create an H2 region spanning dozens of light years. Multiple massive stars forming in the same region create even larger ionized bubbles. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, glows because of a handful of massive young stars at its center, whose radiation ionizes the surrounding molecular cloud. The radiation pressure and stellar winds from young stars don't just make the cloud glow, they also begin to push the gas away, clearing out cavities in the molecular cloud. This feedback can actually trigger more star formation in the surrounding material. As the expanding HII region compresses gas at its edges, it can push that material above the density threshold needed for collapse, triggering new rounds of star formation in a process that propagates through the cloud. Young star clusters often show evidence of sequential star formation, with the oldest stars at the center surrounded by progressively younger stars farther out. The initial generation of stars alters the cloud, compressing and heating gas at the periphery, triggering the formation of the next generation. This process continues until the cloud is either dispersed entirely by the radiation and winds from the young stars, or exhausted of material dense enough to form new stars. The most massive stars, those dozens of times more massive than the Sun, live brief but spectacular lives. They burn through their nuclear fuel in just a few million years, and then explode as supernova, catastrophic events that briefly outshine entire galaxies. These explosions inject tremendous energy into the surrounding gas, heating it to millions of degrees, accelerating it to thousands of miles per second, and enriching it with heavy elements created in the star and in the supernova explosion itself. Carbon, oxygen, silicon, iron, and even heavier elements like gold and uranium. These heavy elements mix into the molecular cloud, changing its composition. The next generation of stars that forms from this enriched material will contain more heavy elements than the previous generation. This process of stellar birth, life, death, and rebirth has been occurring for over 13 billion years, gradually enriching the interstellar medium with heavy elements. The earliest stars in the universe formed from nearly pure hydrogen and helium. Stars forming today, including our Sun, contain about 2% heavy elements by mass, a small fraction, but crucial for the formation of planets, and ultimately for the existence of life. The dust mixed throughout these star-forming clouds plays a crucial role beyond just blocking light. The tiny grains, typically less than a micrometer in size, serve as surfaces where molecules can form. Hydrogen atoms landing on a grain's surface can find each other and bond, forming molecular hydrogen far more efficiently than they could in the gas phase. Water molecules, carbon monoxide, and more complex organics also form on grain surfaces, then evaporate back into the gas or become incorporated into forming stars and planets. Star formation is not perfectly efficient. Only a small fraction of the gas in a molecular cloud, perhaps 1 to 10%, actually ends up in stars. The rest is either dispersed by stellar feedback, ejected by stellar winds and supernova explosions, or simply never reaches densities high enough to collapse. The molecular clouds we observe are continuously evolving, with some regions collapsing to form stars while other regions are being cleared out by the very stars that recently formed within them. Different regions of the galaxy have different rates of star formation. The spiral arms, where gas is compressed as it enters these density waves, show enhanced star formation, lighting up with the blue glow of young hot stars and the red emission from H2I regions. The galactic center, with its extreme environment and powerful tidal forces, has intense star formation, but also extreme feedback that can suppress star formation. The outer regions of the galaxy, with less gas available, form stars more slowly. Star formation is occurring right now throughout the Milky Way and throughout the universe. In distant galaxies, billions of light years away, we observe intense starbursts where entire regions of galaxies are forming stars at rates thousands of times higher than in our galaxy, triggered by galaxy collisions or mergers that compress enormous quantities of gas. The stars forming in those distant galaxies emit light that has travelled across most of the universe's history to reach our telescopes, showing us star formation as it occurred when the universe was much younger. The glowing nebulae we see in telescopes and photographs are not static monuments, but dynamic regions of ongoing transformation. The clouds are collapsing, the protostars are growing, the newly formed stars are dispersing the clouds that gave them birth. Within a few million years, the blink of an eye on cosmic timescales, a star-forming region transforms from a dark molecular cloud to a bright cluster of young stars, to a dispersed association of stars gradually spreading through the galaxy, each one carrying forward the legacy of its birth, enriching future generations of clouds with the elements created during its life, continuing the cycle of stellar birth and death that has shaped the galaxy since its formation billions of years ago. Why gas giants spin at different speeds? The giant planets of our solar system rotate at speeds that seem almost impossible when you first encounter the numbers. Jupiter, the largest planet, completes a full rotation in just under 10 hours. Imagine standing on a world where a single day passes more than twice as fast as the time it takes to watch a long movie. Saturn spins even faster in some ways, though its rotation is more complex. Uranus and Neptune, the ice giants farther out, rotate at their own distinct rates, each with rotational periods that tell a story about how they formed and what has happened to them over billions of years. Picture Jupiter in your mind, a massive sphere of swirling clouds in shades of cream, brown, orange, and red. This giant world contains more mass than all the other planets combined. Yet it spins so rapidly that it bulges noticeably at its equator. If you could somehow stand at Jupiter's equator, you would be moving at over 28,000 miles per hour, far faster than anything on Earth except spacecraft. The planet's day, the time it takes to complete one rotation, is only about 9 hours and 55 minutes. This incredible speed creates winds that race around the planet in alternating bands, some flowing eastward, others westward, creating the distinctive striped appearance we see in telescopes. But here's where it becomes fascinating. Not all of Jupiter spins at the same rate. The planet is made primarily of hydrogen and helium in gaseous and liquid forms, with no solid surface to anchor to. The equatorial regions spin slightly faster than the polar regions, completing a rotation in about 5 minutes less time. This differential rotation is possible because Jupiter isn't a rigid body like Earth. Different latitudes can rotate at different speeds, sliding past each other in the fluid interior. The deep interior, where hydrogen is compressed into a metallic liquid state, may rotate at yet another rate, one that scientists are still working to measure precisely. Saturn presents an even more puzzling picture. This ringed giant is less dense than water. If you could find an ocean large enough, Saturn would float. Its rapid rotation, with a day lasting only about 10 hours and 33 minutes, causes an even more pronounced equatorial bulge than Jupiter's. The planet's diameter at the equator is nearly 10% larger than its diameter from pole to pole. Picture a sphere that's been squeezed from the top and bottom while being stretched around its middle, all due to the centrifugal force of its rapid spin. What makes Saturn particularly mysterious is that determining its exact rotation rate has proven remarkably difficult. Unlike rocky planets, which have surface features that can be tracked, or planets with strong magnetic fields that rotate with the deep interior, Saturn presents challenges. Its magnetic field is almost perfectly aligned with its rotation axis, which makes it hard to use as a reference. Different methods of measuring Saturn's rotation have given different results, sometimes varying by as much as several minutes. The planet's atmosphere rotates at different speeds, at different latitudes, just like Jupiter's. But figuring out the rotation rate of Saturn's deep interior, the true rotation rate of the planet, remains one of the ongoing puzzles in planetary science. The rings of Saturn add another layer to this story. These rings are made of countless particles of ice and rock, each one orbiting Saturn independently, according to the laws of orbital mechanics. The inner parts of the rings orbit faster than the outer parts, completely independent of how fast the planet itself spins. If you could watch from above Saturn's North Pole, you would see the rings spinning like a vast flat disk, while beneath them the planet rotates at its own separate rate. And within the planet, different layers rotate at their own speeds as well. Now travel farther out to Uranus, the tilted giant. This planet rolls through space like a ball rolling along the ground, with its axis of rotation tilted 98 degrees from the perpendicular to its orbit. Something in Uranus's past, likely a massive collision with another planet-sized object, knocked it onto its side. Despite this dramatic tilt, Uranus rotates relatively quickly, completing one rotation in about 17 hours and 14 minutes. This is slower than Jupiter and Saturn, but still far faster than Earth's 24-hour day. The interior structure of Uranus affects its rotation in ways different from the gas giants. Uranus is classified as an ice giant rather than a gas giant because, beneath its hydrogen and helium atmosphere, it contains a much larger proportion of water, methane, and ammonia ices. These materials, compressed under tremendous pressure, create a layered interior that may not mix as freely as the interiors of Jupiter and Saturn. This layering could mean that different depths within Uranus rotate at substantially different rates, though our knowledge of the planet's interior remains limited from Earth. Neptune, the farthest giant planet, spins with a period of about 16 hours and 6 minutes, slightly faster than Uranus, despite being similar in size and composition. Neptune's deep blue colour comes from methane in its atmosphere, which absorbs red light and reflects blue. Like the other giant planets, Neptune shows differential rotation, with its equatorial atmosphere moving at a different speed than the atmosphere at higher latitudes. The planet has the strongest winds in the solar system, with some storms showing wind speeds exceeding 1,200 miles per hour. These winds don't simply follow the rotation of the planet. They race around at speeds that are faster than the underlying rotation rate, driven by heat flowing from Neptune's interior. The question of why these giants spin at such different speeds takes us back to the formation of the solar system. Imagine the early solar system as a vast rotating disk of gas and dust surrounding the young sun. Within this disk, material began to clump together, forming the seeds of planets. As these clumps grew larger through gravity, pulling in more material, they began to spin faster due to the conservation of angular momentum, the same principle that causes a figure skater to spin faster when pulling their arms in. Each growing planet accumulated material that was already moving in orbit around the Sun. This material had angular momentum, and as it fell onto the growing planet, it transferred that momentum to the planet itself. The amount of spin the planet ended up with depended on exactly how this accretion process occurred, the trajectories of the infalling material, the timing of impacts, and whether the material came in symmetrically or from preferred directions. Jupiter and Saturn, being closer to the Sun and in regions with more available material, grew faster and larger than Uranus and Neptune. Their rapid growth meant they could capture enormous amounts of gas from the protoplanetary disk before it dissipated. This gas fell onto the planets from all directions, and the net effect was to spin the planets up to high rotation rates. The exact speed depended on the complex details of how the gas flowed onto the growing planet and how the planet's gravity interacted with the surrounding disk. The spin rates were also affected by large impacts during the final stages of planet formation. When planet-sized objects collided, they didn't just add their masses together, they also exchanged angular momentum. The angle and speed of impact determined whether the collision would speed up the planet's rotation, slow it down, or even change its axis of rotation. Uranus's extreme tilt almost certainly resulted from one or more giant impacts that occurred late in its formation. Inside these spinning giants, the story continues. The rapid rotation creates strong Coriolis effects that organize the atmospheric flows into bands and zones. Rising warm gas gets deflected by the planet's rotation, creating the jet streams that race around the planets at different latitudes. In Jupiter's case, these jets are remarkably stable, maintaining the same patterns for centuries or longer. The rotation also affects the planet's magnetic fields, which are generated by the movement of electrically conducting fluids in their interiors, liquid metallic hydrogen in Jupiter and Saturn, and perhaps ionic water solutions in Uranus and Neptune. The differential rotation, the fact that different parts of these planets spin at different rates, creates zones of shearing where adjacent layers of fluid slide past each other. These shear zones can become unstable, spawning turbulence and storms. The Great Red Spot on Jupiter, a storm larger than Earth that has persisted for centuries, exists in a region where different wind speeds interact. The storm itself rotates, but at a rate different from the planet's overall rotation, caught in a complex interaction between different atmospheric layers. As these planets continue their journeys around the Sun, their rotation rates change, though extremely slowly. Gravitational interactions with their moons cause tidal effects that gradually transfer angular momentum between the planet and its satellites. This process is the same one that has locked our moon so that it always shows the same face to Earth, though it operates much more slowly on the giant planets due to their enormous masses. Jupiter's large moons are very gradually moving away from the planet, carrying angular momentum with them, which means Jupiter's rotation is slowing down. But this process operates over timescales of billions of years. The interiors of these planets remain largely mysterious, hidden beneath thousands of miles of atmosphere and fluid layers. Scientists use the planet's rotation rates, combined with precise measurements of their gravitational and magnetic fields, to deduce what must be happening in the unseen depths. The exact rotation rate of the deep interior tells us about the distribution of mass within the planet and how rigidly different layers are coupled together. Variations in the gravity field, measured by spacecraft flying past, reveal how mass is distributed between the equator and the poles, which in turn reveals how the rotation has shaped the planet's interior structure. Each of these giant worlds continues to spin through the darkness of space, their days flashing by in fractions of an Earth day, their atmospheres swirling in patterns that have persisted for eons. The differences in their spin rates encode the history of the solar system's formation, the random chance of ancient collisions, and the ongoing physical processes that govern how fluids behave under extreme conditions of pressure, temperature, and rotation. Understanding why gas giants spin at different speeds means understanding not just these four worlds, but the principles that govern planetary formation and evolution throughout the universe. Wherever giant planets circle other stars,